Okay, we're going to talk about generics and lists right now. I'm going to sort of talk about lists on the whiteboard and give you the general concept of it, and then we're going to switch to code and see how they actually are basically implemented. It's also a very good way to tie in generics, which will come in after the fact. So I'm going to talk about lists right now. We won't talk about generics on the board. We'll implement the list and use generics in the code. So a list is quite simple. We already know what an array is, right? An array is just something like that. And in memory, it actually winds up being very similar, just something like that. And it's one contiguous chunk of memory. If we add a fourth value here, we would add another value here. That contiguous chunk of memory is important because it actually makes it fast. Every time we need to bring something in from memory to the CPU itself, it's a slow process, relatively speaking. So there's a thing called cache, which goes to speed that up. And when we bring in one part of the array, we typically bring in a lot of it. So if we're going to loop over it, we'll have a bunch of it in cache and it will go much faster. So the idea is to keep as many things in memory as we possibly can, or in cache. Big cache is expensive and it's limited, so that it can't hold everything. Um, but it's faster to access in general in an array. With a list, it's done a little bit differently. It's done through a series of um, references, pointers, through memory. So this could be in one part of memory, this could be in a totally different part of memory, totally different part of memory, totally different part of memory. So if we wanted to loop over it, what we do is we grab this one, brings that into memory, along with whatever else is in memory around it, which may or may not involve the next piece of the list. When we go to get the next piece of the list, it has to potentially, it checks to see if it's in cache. If it's not, it goes and grabs it in memory. Now, the exact same sort of thing happens with an array. Say the array is very large, right? Millions of entries, right? It's only going to grab a chunk of the array at any point in time and put that into cache. So it's possible that these four entries will all be in the same area of memory and they'll all get brought in at once, but it's also entirely possible they're in completely different sets of memory and it has to bring them in. So lists are generally slower than arrays. However, lists have a few advantages. If I wanted to put in 2.5, we'll say, and I wanted to put it in between 2 and 3, all I have to do, through some trickery, is have this one point to that and have this one point to that, and we're done. Right? It's very simple to deal with that. So if I want to insert into any place in the list, it's quite simple. If we wanted to do the same thing with an array, right? We have an array like this. I'll draw it this way this time. Right? There's our array. If I want to insert 2.5, what I have to do is I have to make another array that's actually bigger. And I have to copy the 1 over here. I have to copy the 2 over here. I have to insert 2.5. I have to copy the 3 over here. And I have to put the 4 over here. So I have to, and then I have to reassign the variable. A was pointing here. Now A has to point down here. So it's a much more involved process to insert anywhere I want in the position. Also, I need to, for an array, I need to know how big it's going to be at the beginning. If I don't know that, I'm going to have to keep growing it, which is an expensive process because I have to copy everything from here to there every single time. Even if I just want to add one item to the end, right? So I want to add 5 here. I have to copy 1, 2, 2.5, 3, 4, and then put 5 in at the place I added and point the array at that. So it is a much more involved process in terms of growing or inserting into the middle. So lists are slower in that they require you to do things in potentially use more memory and cause more memory loads into the cache, which is a slow process. Arrays are problematic because if you need to change them, the number of items, or we'll say change the number of items after it's created, it's a much more involved process. So my general rule of thumb is I use an array when I know how big it is, and I use a list when I don't know how big it is. That's the general way I do things. And then when we actually do the code, I'll show you how I really, really, really do things. So there's actually going to be two bits of code. One is going to be me implementing a list, and the other one is going to be me using the lists as I would in Java that already exist. So let's talk about how the structure of a list looks, and this is what I'm going to wind up coding. So every list every list. There's a few different kinds of lists, and there's a number of ways of implementing them. But in general, every list has a thing called a head that points initially to null. Then when we go to add something like the number 1, we'll make a node 1. It will have this thing called a next pointer, or next reference, and it will point to null. And that will make the head point to that one. If we want to add 2 to that, same process. We have head, it's pointing to 1, which is pointing to null. And we're going to add the number 2, which is pointing to null. And all we need to do is say that this one here points to that one there, and it's added. And add another one, same thing. We just make a new node, 3. It's by default pointing to null. And we'll make this one no longer point to null. We'll make it point to 3. And so on and so on and so on. If I want to put in the number 1.5 in between 1 and 2, we'll make a new node. It will point to null. Now things get a little more tricky. What I have to do is I have to say 1.5 points to 2. And 1 points to 1.5. And that order is super important. Okay? If I do it in the wrong order, if I say 1 points to 1.5, I now have no ability to point back to 2, right? So when we look at the code, you'll see me mention how important it is to get this done in the right order. It's really important to get it done in the right order. We've now broken our list. We can't get to 2. It's lost forever. So we want to make sure that what we do is, especially when we're learning linked lists, we want to make heavy use of these pictures to draw, okay, this is the behavior I want. Now, how do I actually get that? Another thing that often happens with linked lists is you have another variable, tail, which simply points at the back, and everything has a previous pointer that points, or reference, that points back to the one behind it. So if we want to add to the end, it's really simple. We just add to here. Otherwise, think about if we didn't have this previous stuff and we wanted to add the number 4 to the end. Oh, sorry, put that in the wrong place. What we're going to have to do is we're going to have to go from head to 1 to 1.5 to 2 to 3, and then say, okay, 3 no longer points to null. It points to 4, 4 points to null. If instead we have this tail thing, all we have to do is add our 4. It points to null. Make the tail now instead point here. And before we had done that, we wanted to make this point to 3, so we don't lose it. And again, I'll show you both ways of doing that in the code. But these pictures become super, super important. Okay, but that's all a list is. A list is very simple. It's just one thing pointing at another thing. If we were in person, what I would actually have you do is line up as a class and figure out yourselves alphabetically and just literally point to the next person. And then I'd ask your name and we get you all in alphabetical order, right? All I need to know is who the first student is, and I can get to all of the other students. In an array, I'd literally just line you up. So if with a list, you can all say seated wherever you are, as long as you're pointing to the right person, I know where to go next. With an array, I'd literally line you up against the wall and then just go down the line asking each one of you what your name is, right? And you'd have to sort yourself alphabetically. So an array has to be contiguous. A list can be all over the place. We could even point to a whole other classroom to get to the next person, right? We're not limited to where we are in the physical space. So lists jump all over the place. Arrays, nice big contiguous thing. Lists, easy, relatively easy to insert into the middle or add to the end. Arrays, hard because you have to grow it and copy things, right? Think about, we have all the students in an array lined up in alphabetical order, and a new student joins us. I have to insert them into the right part of the line. And to do that, everyone has to shuffle down. With a list, we just have to change who we're pointing to. Much quicker. So use arrays. My view is use arrays when you know how big the data is. Use lists when you don't. And in reality, it's actually a combination of the two, but we'll talk about that when we actually look at the code.
Alrighty, so the code for lists. So I'm going to make a very simple list. It will not be as complete at all as the one that Java contains. Java contains its own list class. Most languages have something like this, not all of them. And I'm going to make a class called node. And we'll improve upon this in a later date. I'll reuse this code for something else. So in node, we're going to make our list hold ints. So there we go. This is one of the cases where I'd said if you have no other reason, make an interface, an abstract class, subclasses. This is what we would call a value class, and there's no point in creating all of that hierarchy. It serves no purpose. This is just a class. It holds something. It's never going to be used in any polymorphic sort of sense. It's just kind of like your wallet and how it holds credit cards, right? It just holds a value for some things. There's no behavior in here. It's just a data storage. It's a data class. So no need for any of that. And list, on the other hand, yeah, an interface and abstract class, that would make total sense, but I don't need to do that for this example. But in reality, yeah, I actually would make a list and interface and all that kind of stuff. And again, we'll look at the way Java's implemented this, and that's what they do. We'll look a little later. So I said every list has a concept of a head node. I won't bother with the tail stuff right now. We can come to that after. That also means that the node needs to have a next. Have get next, and we'll also give the ability to set it, because remember, we want to be able to change where it's pointing to. So we can insert into the middle of it. So now we have the ability to chain nodes together. Each node knows about the node that comes after it. And the list knows about the very first node. So again, going back to our student example, this is the head is going to point to the student with the first, if we're doing alphabetically, by first name, the person with the alphabetic first name. They're then going to point to the next person with the, so we've got Alice and then we've got Bob. Right? And Bob's going to point to Charlie, and Charlie's going to point to Dana, and Dana's going to point to Edward, and Edward's going to point to Felicia, right? So that kind of thing, right? So there's not really much we need to do in a constructor. The head is going to point to null. That's what we want. The same with node. The int value we have to set, and the next node is pointing to null. That's what we want. So there's no constructor needed. But we want to be able to add. So I want to add an int to the list. So what that would look like over here in main I'm going to add the number 1. And then we're going to add the number 2, and then we're going to add the number 3. Then we're going to add the number 5, and then we're going to add the number 4. So they're out of order, but that's okay. Nothing says they have to be alphabetical kind of thing, or numeric or whatever. So what I'm also going to do is going to add a toString. You should use toString for debugging purposes. That is the gist of it. I have used an API once that actually used toString to display something, and it was horrible because my display got all wrecked when I went to override toString to print out my debug information. All of a sudden, my UI was filled with all this debug information. Not what I wanted. Was not happy. So that's what toString is for. And we should always add the override, even though it's not strictly needed. And what we're going to do is, for now, we'll just return head dot get value. Oh, it doesn't like that. There we go. That's what I meant. Value of. I think we can just give it that. There we go. So it's going to convert the int into a string for us. So what we're going to do in main is we're just going to print out the list after each one of those so we can watch it grow. Obviously that's not going to happen yet because we're not actually doing anything with the list to see that, and it's actually going to crash to begin with, but let's try it anyways. So yeah, it crashed. Crashed in toString. The reason it crashed in toString is there's no value for head. Head is pointing at null. So if head equals null, otherwise we'll grab it. Now this isn't going to work very well, but it won't crash to begin with, so that's good. Right, so if our head is null, which by default it is, the only way we can change it is when we add something, and add isn't doing anything yet, so head's always going to be null for now. So if head is null, we're going to print out null. Otherwise, we're going to print out the value of the first item in the list. So it's not going to be very interesting, it's just going to print out null a bunch of times because we're never changing what it points to. Okay, so how on earth do we make this work? Well, let's try something really dumb. It's not going to work. Head is assigned. Let's actually make this. We'll make our new node, and we'll make the head point to new node. And let's see what happens. It'll be different. It still won't be correct. Okay, so now our list only ever has one item in it. First it has nothing in it, then it has 1, then the value 2, then the value 3, then the value 5, then the value 4. It's not actually making a list out of them because we're just changing where head points. So think back to the drawing if you need to pause the video and go back to the drawing. we want to draw that out. I'm going to try and draw it out inside of the code here. It doesn't work as well, but right now we have head pointing to null. What we want is head to point to the value 10, and that to point to null. Right? So the simplest way to do that is if the head equals null, then the head is assigned new node. Otherwise, this will also not be correct, but I'm doing a little bit at a time. What do? We want to make the head, so we come in here, head is equal to null. So that's this case. And what we want to make is the head point to the new node, which is a value of 10, right? And we've got that. So what happens when we add another value, like, we'll change it to 1 to match the stuff we're doing in main, right? So what happens when we add 2? Well, what we want the list to look like now is head points to 1, which points to 2, which points to null. But what we're getting right now is all we're doing is changing this to 2, right? So that's not right. So the simplest way to make this is say that the head dot next, right? That gets us the 1. Set next to the new node. So now what we should get is we should print out 1 and 2, and then 1 and 3, and then 1 and 4, and 1 and 5, because we're only ever changing this one now. Sorry, that should be, no. Oh, sorry. We just need to do head.set next. My mistake. Because 1 is head. Sorry. 1 is pointing at head. So when we're saying head, we're actually saying 1. So it doesn't crash, but it still only prints out 1 because we're never actually printing out the next one. So we actually have to start doing a loop here. So think about it again. We're pointing at something that looks like this. And we want to add it up. Now, the problem I have doing what I'm doing here right now is I'm hard coding it to only work with 2 values, right? Before it worked with no values and 1 value, now it's going to work with 2 values. Obviously, I want it to work with any number of values. I can keep adding these forever until I run out of memory. So I can't just hard code this continually because it won't work. I have to make it dynamic. In order to make things dynamic, typically it's going to be a loop. One important thing, I don't ever want to modify my list when I'm printing it out, so I'm going to need a temporary value. So we usually call that temp node. And temp node is assigned head. And then we're going to say, well, temp node is not equal to null. We're going to grab each value from the temp node now. So we're going to grab 1. Right? So right now we say temp node is assigned head. Well, the temp node is not equal to null. I don't know what this is going to do. Let's see. Oh, no. That's wrong. It's just because I haven't finished the code yet. So we're going to, so temp node is pointing at head. Head is actually pointing out, head is referring to 1. So 1 is, there's a node there. It's not equal to null. So we're going to grab the value. We grab 1. We get it as a string. And we're going to say retval plus equals the value. I'm going to show you a better way to do that. And retval can no longer be final because we're changing it inside the loop. And retval has to start off with the value. of nothing. And it doesn't like this, and I will show you a better way to do this. And then so now we've gotten the value 1, now we want to advance to the next one, so all we have to say is the temp node is assigned the temp nodes get next. So that advances us, so if we had this temp node, it's pointing at 1. Then it's going to point at, so I'll do it like this. Where's that key? Key I rarely use. There. So it looks like something like that. It's pointing at 1. Then temp node is going to point at 2. And then temp node is going to point at 0. So it'll just loop through those. So now when we run it, right, we get 1 and 2, 1 and 3, 1 and 5, 1 and 4. The problem here is, hopefully you've realized, we didn't do the same kind of loop over here. We just set it to the next. So this is simple as well. We can actually steal this general code here. Don't need the R value. Don't need this value. Don't need to get the value. Don't need that. We do need that. So actually it's going to be, well, the temp node get next is not equal to null. We're going to keep going. So this is going to keep going until we reach the last node. So we're going to, this is where we have right now. So we've got the number 1, there's a node there, and the temp node's next is null. So we're not actually going to, we're not going to execute this. But let's say we want to add 3. So we're going to start off pointing at 1, and the next one, the get next, is not null, it's 2. So we're going to go to 2. Now 2 is, sorry, we're over here. 2's next is null, so we're going to stop, and we're left at 2, and then we can just do our addition, which was quite simply temp node dot set next is the new node. So hopefully now we'll actually print out our whole list. Yay! There it is. Yeah. So I want to show you this this thing here. We're going to make this final again. I'm going to make a string builder. This is not quite the same as the, sorry, I've got a little bit out. This is not quite the same as the builder pattern, but it's not far off. I guess, technically, I guess this is the builder pattern. It's not what I would consider the builder pattern, but you know, it does let you build a string. So I guess it technically is a builder pattern. So we're not going to set the ret value. We're going to set the builder to a new string builder. And here we're going to do builder.append the value, and we're going to append a comma. And we're going to say that the ret val is assigned the builder.toString. So using the string builder is preferred over doing the plus equals. The only thing I don't like is I have this trailing comma. It's actually really easy to get rid of. All we have to do is say the builder dot set length is the builder dot length minus 2. So why minus 2? 1, 2. So we're just taking off the last comma in space. If we didn't do that, you see there's a space and then the comma. So you can't even see it, but it's there. So we'll just get rid of them. So there we go. That's a simple implementation of a linked list. I'm not going to go through the whole linked list, but that's a very simple one. And the next thing I'm going to do is I'm going to turn this into generic. So we'll stop the video there, and I'll make a new video on the generic side.